Hey everyone, today we're going to finish talking about section 2.2 and then we're going to talk about section 2.3. I actually erroneously have a section 2.4 here. That doesn't actually exist in your text, so you can just ignore that. So the first thing that we're going to do is we're going to pick right back up from yesterday's class where well, I guess maybe that doesn't make too much sense if you're just watching these videos, but we finished by talking about frequency distributions and drawing histograms. So today we're going to start out by talking about relative frequency distributions. So while frequencies are helpful, understanding the relative size each class is to the total is also useful. To find this, you divide the frequency by the total to create a relative frequency. If you have all the relative frequencies for all of the classes, then you have a relative frequency distribution. So here at the top, we have a nice definition for relative frequency distribution. This is a variation on a frequency distribution, is a relative frequency distribution. Instead of giving the frequencies for each class, you calculate the relative frequencies. So again, relative frequency is just frequency divided by number of data points. A relative frequency gives you the percentages of the data that fall in each class, or the proportion of the data that fall in each class, depending on if you convert this decimal that we receive to a percentage or not. Starting out with the table that we ended yesterday's discussion with, let's just look at an example of how to calculate the relative frequencies. I'm told that relative frequency is number of data points, or a frequency divided by number of data points. So, the relative frequency of my first class, in that case, would be 4 divided by, let's see, the number of data points here is 4 plus 8 is 12, plus 5 is 17, 23, 24. So 4 over 24, this is, if we put this in a calculator, this is like 0.1667. This decimal repeats, but we can round this off. And this is the relative frequency for my first class. For my second class, I perform the same calculation. I take the frequency, which in this case is 8, and I divide it by the total number of data points, which is 24. So 8 over 24 is 1/3, or 0.333, and this repeats. So this is my second relative frequency. And we continue on for each of our classes until we get a table that looks like this. Here we rounded off this first one to just 0.17 instead of 0.1667. So here we have all of the relative frequencies listed next to the frequencies in this table. Notice that the total here should add up to 1. Or if you write these as percentages, they should add up to 100%. Although they could be a little bit off if you have some, if you did some rounding. The numbers could be a little bit off due to rounding errors. The graph of a relative frequency distribution is known as a relative frequency histogram. This actually looks very similar to the histogram that we looked at yesterday. It actually looks identical to the frequency histogram, but the vertical axis is now relative frequencies instead of frequencies. So, if I compare this, Notice here on my y-axis, I have relative frequencies. Let me grab the histogram from yesterday's class. Notice that these two actually have exactly the same shape. The only difference between these two graphs, other than I guess the visual difference of they have slightly different colors and one's a little bit clearer than the other, is that on the right graph we have relative frequencies in the y-axis, whereas in the left graph we just have frequencies in the left axis. Other than that, these are the same. Oh yeah, I suppose the labeling on the x-axis is also different between these two, but that's not a problem at all. The labeling on the x-axis in the second one is simply the midpoints of each of these classes. We're still going by the same, the first graph is still created with the same data, right, just with frequencies. And instead of listing the midpoints of each of the classes in this left graph, they simply start at 500 and then increase in $500 increments from there. So another useful piece of information might be how many data points fall below a particular class boundary. For instance, a teacher might want to know how many students received below an 80%. A doctor might want to know how many adults have a cholesterol of below 160. A manager might want to know how many stores gross less than $2,000 per day. This is known as a cumulative frequency. So this idea of how many data points fall below a particular class boundary. This is what we call cumulative frequency. If you want to know what percent of data falls below a certain class boundary, this is what we call a cumulative relative frequency. For cumulative frequencies, you're finding how many data values fall below the upper class limit of this lowest. You want to find how many data values fall below the upper class limit of whatever class you're talking about here. So again, we want to figure out how many students receive below an 80%, or how many adults have a cholesterol below 180, or 160 rather, sorry. So to create a cumulative frequency distribution, count the number of data points that are below the upper class boundary, starting with the first class and working up to the top class. The last upper class boundary should have all of the data points below it. Also include the number of data points below the lowest class boundary, which is 0. So we're going to create a cumulative frequency distribution for this data. This was the student rent data that we looked at previously. So when doing this, we want to ask ourselves how many data points fall below each boundary. So below 349.5, there are 0 data points. Right? Below this lowest lower class boundary, there are 0 data points. Below this next lower class boundary, there are 4 data points. Below 979.5, there are 4 plus 8 data points, which is 12 data points, and so on. we continue this process until we reach the upper class boundary. Let's see, do I have the snippets of our code here? I do not. This is what our table will end up looking like once we create this cumulative frequency distribution. So again, notice that this is just telling us how many data points fall below each of these class boundaries. So within this first class, we just have 4 data points. So our cumulative frequency here is 4. At the next step, we've added another 8 data points, so our cumulative frequency is 12. And we just keep repeating this process. We just keep adding the frequency of each row of each of these classes to get our new cumulative frequency. Notice that our cumulative frequency doesn't change for 2 of these classes because 2 of these classes have 0 data points in them. Now, what would a graph of something like this look like? Let's check it out. This is the graph for a cumulative frequency, and this is called an ogive. To create one of these, you want to create a scale on both axes that will fit the data, and then you want to plot the points of the upper class boundary versus the cumulative frequency. We want to include the point with the lowest class boundary and the 0 cumulative frequency. And from there, we just want to connect the dots. So all we did here was take this exact graph, we have points on the x-axis that are the upper class boundaries. So on the x-axis here, we have, what is this, 664.5. Then this one's going to be 979.5. 1294.5, 1609.5, 1924.5, 2239.5, and 2554.5. So from here, we plot all of these upper class boundaries versus the cumulative frequency at each of these upper class boundaries, which you can again find from this chart. The usefulness of an ogive in this case is to allow the reader to find out how many students pay less than a certain value. So this may be an easier way of visualizing this than simply looking at a chart. If you graph the cumulative relative frequency, you can find out what percentage of students are below a certain value instead of the number of people below a certain value. Another big idea that we want to look at here is this idea of shapes of distributions. When we look at a distribution, we want to look at the basic shape of the distribution. Now, obviously, we are going to have to talk about this. Well, you could maybe kind of visualize what something might look like or get an idea of it from just looking at the numbers. But typically, we're going to have to look at a graph to do this. There are some basic shapes that are seen in histograms, although some distributions do have no shape. Some common shapes are called symmetric, skewed, and uniform. Skewed is, sorry, I started one low. Symmetric is whenever you can fold the graph in half down the middle and the two sides line up. So the two sides are mirror images of each other. Skewed is when one tail of the graph is longer than the other tail. In this case, we say that the graph is skewed in the direction of the longer tail. Uniform is whenever all of the bars are the same height. Exactly the same height. Notice that, I guess the uniform would also imply that this is symmetric, right? Uniform things are going to be symmetric as well. Another interest is how many peaks the distribution has. This is what we call the modality of the graph. So unimodal is whenever it has one peak. Bimodal is whenever it has two peaks. And if a graph has more than two peaks, the modal information is no longer of any interest. A few other important features that we want to look at are gaps between bars, like whenever we saw our histograms here. Notice that there's a large gap between our bars here. A repetitive pattern, how spread out the data is, and where the center of the graph is. And we're just going to look at a few examples of these graphs that we just discussed. So here in the top left, we have a roughly symmetric graph, right? The two halves are approximately mirror images of each other. Notice that it's not perfect, right? This bar is a little bit higher than this bar. And this bar over here on the left, it looks like it's a little bit higher than this bar over here on the right, right? It's not exactly perfect, but we would say that this is about, this is roughly symmetric. So typically we would refer to a graph like this as being symmetric. The graph right below it has two peaks, so we say it is bimodal. This graph is also symmetric. It folds, you could fold it in on itself and it would overlap perfectly. All the edges would line up. The two halves here are mirror images. We also have skewed right and skewed left graphs. Again, we say that a graph is skewed in the direction of the longer tail. So in this skewed right graph, notice that the right tail is longer, so we say this is skewed right. Down here, we see that the left tail is a little longer, so we say that this is skewed left. And here we have a uniform graph. All of the bars are the same height. And from here, here's an example that is from my Open Math. This says that data was collected from 300 fish from the North Atlantic. The length of the fish in millimeters is summarized in the GFDT below. And by GFDT, we mean grouped frequency distribution table. So whenever you see this, This is really just referring to a frequency distribution table. This is grouped frequency distribution table. Ooh. And the question here is, what is the lower class limit for the fourth class? Here we just want to determine which class is the fourth class, first of all. And to determine this, we just go down the list here. 1, 2, 3, 4. So this is my fourth class. From here, I just want to say, what is the lower class limit? Well, the lower class limit is just this 105. Moving on to the next one here. Here we have a frequency distribution, and we want to find the cumulative frequency for the class with lower class limit 31. And to do this, let's see, the class with lower class limit 31, let me change to green here, is this class. So we want to add up all of the frequencies from this class and everything before it. So I want to add up all of these numbers. So this is just 8 plus 3 plus 7 plus 5 plus 7. This is 11 plus 7, which is 18, 23, 30. So the cumulative frequency for the class with the lower class limit 31 is 30. And for this third example, we're given a frequency distribution, and we want to find the relative frequency for the class with the lower class limit 27. Here we want to find the relative frequency. So notice this is important, and this is why I captured the answer box, that this has a percentage next to the answer box. The answer box here in my open math has given us a percentage sign. This means that your answer shouldn't just be this number that we calculate. We need to make sure that it is in terms of a percentage. So whatever decimal we get, we're going to have to multiply by 100. So to find the relative frequency for the class with the lower class limit 27, let's see, this class has a frequency of 8. So I need 8 divided by the total. And the total frequency here, the total or the total number of observations here, or number of data points, is 8 plus 9 plus 4 plus 8 plus 5 plus 5. So here we have 17, 21, 29, 39. I get 8 over 39. And whenever I type this into a calculator, I get 0.205. But this is not a percentage. To make sure this is a percentage, I take 0.205 and I multiply this by 100. So I get 20.5%. And I want this to be my answer. All right, and that's it for 2.2. I'll start a new video for 2.3, which should be pretty short.